In our previous lectures, we have seen how to calculate the potential due to a charge distribution. And in those lectures, I have told that it is easier to calculate the electric potential because it is a scalar quantity and we need to calculate only one expression for the potential, as contrast with the calculation of electric field, which is a vector quantity, and we need to calculate three components of that vector quantity. However, I also pointed out that it will be easier to use Gauss law whenever it is feasible to use some kind of symmetrical conditions in the given problem. So whenever there is no symmetry, the better way is to calculate the potential, and from that we can calculate the electric field. So let us do some examples to calculate electric field from the given expression of the potential. So in one of our previous lectures, we calculated the potential due to an electric dipole. So let us say this is an electric dipole which is lying about the z axis, and we derived a general expression for the potential due to the electric dipole, which was minus p dot gradient of 1 by r and whole divided by 4 pi epsilon naught. So this is the expression of the potential due to this dipole at a point P, which is at a distance r. Now, how to calculate the field from this? So for that, what we will do, let us say this is cos theta angle. Now we know that gradient of 1 by r is simply minus ar over r squared. So I will use this. So potential due to dipole will be minus qd, and this minus sign will be cancelled out through this ar over 4 pi epsilon naught r squared. So you see that the potential of this dipole is falling with 1 by r squared as compared to a point charge which fell just by 1 by r. So the potential due to dipole falls very steeply compared to a point charge. So now we will further simplify it. So you see that this dot product will give you cos theta. This is angle theta here. So it will be qd cos theta over 4 pi epsilon naught r squared. Now we need to find the electric field. So E is equal to minus of del V. So it will be minus of dou by dou R of this potential qd cos theta over r squared, and this will be the component AR minus dou by r. Somewhere I have used small r, somewhere I used capital R. I am using them interchangeably, so don't be confused with this. Dou theta qd cos theta by r squared. This is component a theta in spherical coordinates. Now you see there is no phi component, so dou by dou phi of this will give you 0. So I will not write that expression. So only the field will have two components, the radial component and this theta component. So now let us solve it further. So it gives, so this is qd cos theta will come outside, and we will be left with minus dou by dou r of 1 by r squared, and this will give you the r component, and in this r squared will come out, so r into r square, and qd will also come out, cos theta a theta. So on solving it, what we will get? We will get, and there is 1 by 4 pi epsilon naught outside all this. So we will get 1 by 4 pi epsilon naught QD, and this will give you twice of cos theta over r squared, and this will give you the AR component, the radial component, plus QD sine theta over r cube. This is r cube, not r squared on differentiation, and this is the theta component. So we will further simplify it by using notations of the dipole moment. So what we will have? We will have 1 by 4 pi epsilon naught. Now QD can be replaced by the dipole moment magnitude, twice of P cos theta over r cube AR plus P sine theta over r cube A theta. Now this P can be taken outside. So what I will get? P by 4 pi epsilon naught. The radial component is twice of cos theta over r cube, and the theta component is sine theta over r cube. So you see that the field is dying with 1 by r cube speed, as compared to a point charge which decayed with 1 by r squared. So you see the field due to an electric dipole will die down much faster than compared to a point charge. So this is one of the property of the electric dipole. Okay, so from this example we have seen that how easy it is to calculate electric field if we know the expression of the potential. Now let us do one more example, and this example is totally different, which is found in usual textbooks. I have taken this from the Feynman lectures of physics. So as you know that electrostatic shielding is provided by conductors, which we have seen in our previous lectures. However, you will find that in many of these shielding concept, you might have seen Faraday cage also, like that Faraday cage is not completely enclosed by a full conductor. However, it is made of some kind of grills or conductor which is not totally fully covering this thing. Like we make a case with these kind of grids or meshes. So we have seen that a full conductor is capable of giving electrostatic shielding. But how do we know that this Faraday cage, which is made of these kind of shelves, can be able to give us the electrostatic shielding? So now let us see a little bit in detail. Let us say that we have a mesh of conductors making, let us say, Faraday cage, and I am assuming for simplicity, let us say this is x direction and y direction is inside the paper, and let us say this is z direction. So for simplicity, I am assuming that these conductors are very long in y direction. Okay, so we will not bother about the change in y direction. We will just bother about the change in x and z direction. Let us say the grid spacing is A, and I am just assuming that these conductors have positive charge on them. Let us say these grid conductors are positively charged. So you see that the potential in this z direction will follow some kind of pattern like this. So near the conductor, because of this charge vicinity, it will have little higher potential. However, when I will move away, this change will be less, it will be more slow, and over some distance it will start to flatten out like this. So at some point it will just behave like potential will be just simply equipotential surface will be like this. So in this way we can see that this potential is some forming some kind of periodic shape. So you see from Fourier series, any periodic function can be represented by sum of sinusoids. So let us say that this potential, which will be a function of x and z only, because there will be not much change in y direction since we have taken very long conductors in y direction, is a function of, let us say, some z, and it is having this periodic variation in x direction, and I can represent it as, let us say, some form of Fourier coefficients. So you see that potential is being represented through some kind of sinusoids, and let us say this is the nth harmonic of this thing. Now we know that at a point when there is no charge, so from the Maxwell's equation, del dot E is equal to rho by epsilon naught, and when this is equal to 0, and when I put E is equal to minus del V, this will be equal to 0. It implies del square V is equal to 0, or del square phi, if I am using phi instead of V as symbol, is equal to 0. So you see, this is a Laplace equation which we will study in future in more detail while solving it. So we can see that this potential is going to follow this Laplace equation whenever there is no charge in the region. So what should this function follow? It is simply dou square by dou x square of this phi n xz plus dou square by dou z square of phi n xz should be equal to 0. Since there is no variation in y, so that third term will be 0. Okay, so from this Laplace equation we can see that we will have minus 4 pi square n square over a square cos 2 pi nx over a, some function of z for the nth harmonic. Similarly, d2 square of the function of z, dz square, and cos 2 pi nx over a is equal to 0. Now this equation is having solution of the form f and z is equal to some a and e minus z by z naught plus b and e minus z by z naught, where z naught is simply a by 2 pi n. Now you see this will be plus sign. This bn must be 0 since potential should fall to 0 at infinity, and to make this 0 at infinity the only requirement can be that this bn is 0. So you see that this nth harmonic fn will be some kind of this form. Now you see, if I put the value of z naught, it will be simply minus 2 pi n over a z. This is the variation part which is depending upon the z. So what, this was the grid which was having spacing a, and this was z direction. Okay, so let us take the first harmonic component. So it will be something A1E minus 2 pi Z by A. So if I just move by 1A, you are going to see that this decreases by minus 2 pi, and it is about some 520 times. So you see, within just a spacing of this grid, the potential, these harmonics are going to die down very fast. Even the first harmonic is going to die down with this speed. So further harmonics are going to die down with much higher speed, okay, or rate. And further, we know that this zeroth harmonic is still there, which is simply minus E naught Z, which is the DC component, or you can see from our derivations of the electric field due to conductors. So you see that after a few spacing, let us say some twice of A or 5 times of A, this grid is going to behave simply as a plain conductor instead of a grid. For a person who is seeing this from this some few times of this grid spacing distance, he will find that this is acting like a full conductor instead of a grid. So in this way, we can see that a grid is going to give us electrostatic shielding, which is similar to a full conductor. So what are the benefits of this? The benefit is that if I use a full conductor instead of a mesh or grid, let us say this is a full conductor, it will give you weight, and of course cost will be higher because of the high material cost. However, if I use just a grid, the cost is reduced and weight is also reduced, and fabrication is also easier. So that's why whenever we require electrostatic shielding like Faraday cage, you might have seen so many videos on YouTube for Faraday cage. It is made by just grids of conductor, and it is not made by just full conductors. So this kind of cage is made by using grids of conductors, and the person is well inside this grid, so he does not feel the effect of any electric fields outside. So in this way, electrostatic shielding works whenever if we use only grids instead of a full conductor. So if you find that this lecture is helpful to you or interesting to you, then please share and subscribe our YouTube channel. And we have created a Telegram channel for doubt discussion, which you can join for with the link given in the description of this video. Thank you.